So you may wonder why you're all here. It's nothing at all to do with climate change. It's just that the Howard Foundation is sponsoring 6 meetings in this theatre so as to promote the idea of it being used for conferences. And if you enjoy the meeting today, as I hope you will, then remember the next time you want to organize a conference, think Downing and look at their website. But I think you'll enjoy it here. Now, I have had a personal interest in climate change over the last 4 years, and I've read the books, I've seen the Al Gore movie and so on, and I've read all the different versions of what people say. And I've listened, and I feel rather appalled at what is happening. I think that, science is is not a religion. It's a matter of discussion. Unless we actually discuss things, we can't make any progress. And science is based on criticism. And you may remember that the astrophysicists had a field day in the old days when Martin Ryle and Fred Hoyle had great debates. But nobody ever called Fred Hoyle a Big Bang denier, because he actually invented the name, as you know. Now, I think that because this is a scientific meeting, we want you to behave. In other words, this is not going to be like Prime Minister's Question Time. You saw the last one, I think, about 2 days ago. Well, Michael Winner is an old boy of the college, and he's the one that promoted, calm down, my dears. But we forget about all that. But do please remember to plead in the questions and comments that to attack the ideas and the data, but not the man. And I think if we do that, we'll have a much more interesting time. Now, I do want to, and by the way, if anybody mentions ClimateGate, they'll be evicted. That's just what I want to say. Now, lunch downstairs you can get, if you haven't got a free ticket, it's £15, and you can, when we had the last conference here, people sat outside on the wall. It's a nice day. It's going to be 22 degrees, according to the Met Office. And we believe everything they say, of course. Anyway, if speakers have, before each session, it's important to hand your memory stick to Martin at the back. But most people know that and have done it already. But anyway, can I open the conference by saying, let's battle commence. Okay, first speaker. It's Phil Jones.
Thank you, Alan. I think you all know who I am. I have, just as a remark, I have not seen Al Gore's movie. I'm going to talk today about the measurement of global temperature. And when I mean measurement, I mean instrumental records with thermometers. I'll be talking about the land and the marine component. There's obviously 2 parts to it. And the marine is more important because it is 70% of the Earth's surface. But I'll start with the land stations, and I'll talk about our homogeneity assessment in trying to make sure that the records from the land stations are telling you things about the past climate and not about the way we've taken measurements over time. I'll separate those into a couple of categories, and one of which will be biases. And these are where the issues are more pervasive in that they affect more of the data. So I'm talking here about the exposure of thermometers. So now they're in new things now, but they're automated. But in the past, they've been in louvered screens developed by Stevenson in the 19th century. But before that, they were exposed differently, and that can lead to problems. So there's a potential problem, particularly, and I'll come to that later, in summers. And then there's the urbanization issue in that what might have been a small rural area or a small town in the 19th century might be a big city now. I'll follow this concept through with the biases in marine records, and particularly the change from the way we've measured sea surface temperatures with buckets in ships up to the Second World War, and from engine intake measurements more after that, and the more recent change to measuring using buoys. And it's quite good having to give this talk in Britain, and you can use the word buoy, having to not pronounce it differently for the Americans. And then I'll move finally on to how we interpolate the data to regular grids, which is how most people want to use the data, and then comparisons with some other groups. So a lot of the data we use is we set it to as a departure or an anomaly from a base period. And the base period we use is 1961 to 90. So this means that if the station series does not have enough data during that period, it will not get used. And so effectively all the data is reduced to anomalies from this period. So every time series you'll see, it's as departures or anomalies from that period. Changing the base period, all that does is just move the series up and down. It may change things slightly locally, but on the large scales, hemispheric and global scales, it will not change things barely at all. Now, I mentioned about this word homogeneity, which means consistency through time, so that you can directly compare a measurement we made today with one that our forefathers might have made 100 years or 150 years ago. And the reasons that these problems come about is that are listed here. So the locations where we measure the temperatures have changed. A lot of sites have moved from city centres, which might have been an observatory in the past, to an airport. I mentioned the designs of Stevenson screens have changed, or they were introduced in the 1870s. The times you measure temperatures have changed, and I'll bring that in a bit with the example of the US. And also over time, the methods used to calculate monthly mean temperature have changed. In Britain and in many other English-speaking countries, we tended to use the mean of the daily maximum minimum, but a lot of other countries have used the measurements based on fixed times during the day. And there wouldn't be a problem unless people changed. A lot of countries have changed. Another issue is the changes in the environment around the station. So, as I said, it might have been a small town in the past. It's now a big city. So this may be an issue, and I'll come with some examples of that. And the urbanization issue as classing as a bias, and exposure with the change in screens as a bias, whereas all the others are adjustments to data for these site moves, observation time changes, etc. They're essentially random through time. They're not consistent, whereas the biases are more pervasive and so can have a bigger influence. This is some work we did in the Climatic Research Unit in the 1980s, and this is a histogram of the adjustments to the temperatures that we did. So 0 here, you wouldn't expect to adjust temperatures by about 0. So these are where we've reduced the temperatures in a series, so they're negative, and this is where you increased. And this characteristic bimodal distribution where you get temperature adjustments between about -3 and +3, and the overall average is about -0.18. But overall, this doesn't really have any effect on the global average because these are occurring at different times at different places. This is just the sort of combination of them all. And this is just some similar work now for the United States. We're splitting it into maximum temperatures and minimum temperatures. And again, you've got these differences where there are positive adjustments and negative adjustments. And these are for all the change points that they found. So change points, the discontinuity or non-homogeneity in the sense I was using earlier. Again, the average is relatively close to 0. These are the ones that are undocumented in their station history information, and these are the ones that are documented. So again, you've got this bimodal distribution. Effectively, what this means is that the adjustment procedures are not adequate to find this central area, and so really the adjustment is really a unimodal distribution, but a lot of the adjustments are very small, and you'll not be able to find them with the networks we have. So overall, the effect of homogeneity adjustments is negligible, and what matters are the biases, and I'll move on to these biases now. So I'll come a bit later to in terms of importance, The most important bias in the data is the adjustments of sea surface temperatures. I'll come to that later. Then you've got the exposure of the thermometers. This is caused by the developments of Stevenson screens in the period before and how it influences summer temperatures, particularly in Europe. And it can have influence in other parts of the world. It's important in Australia before about 1910. It's probably also important in some parts of Russia as well, where the records go back into the 19th century. There's a lot of work going on in looking at these data, and a lot of there's one particular study here by Böhm has adjusted all the data for, this is the larger alpine regions, and there's another study doing the same thing for Spain, and I expect more studies will do this. And the effects of these studies are to lower summer temperatures from about May to September on average by about 0.4 degrees Celsius. Be slightly larger probably in July and slightly less around May and August and September. And there's a slight opposite phase change of the order of 1/10 of a degree on the winter temperatures. But this is only really for the period pre the Stevenson screens or the white louvered screens around thermometers. Then there is urbanization. I'll show you some examples of that in a minute. And a bias that's particular only to the United States is the time of observation bias. Throughout the 20th century, recording in the US, particularly by the non-Met Service sites, which is a large number of, like there is here, there's tendency to have been observations taken in the evening. And by using maximum minimum thermometers, when you switch then to the morning observations, you tend to have a warm bias to the evening observations compared to the morning ones. And there's a lot written about this, and there's an adjustment procedure for the US for this. It's larger in the interior of the US, and it's smaller around the coast. So I've mentioned this is a repeat of this. So it's going to, the adjustments for the exposure are going to be this sort of order, about 0.5 degree. What we do with urbanization is we incorporate that into this error. And these error terms are going to go into the, with the homogeneity adjustments, they're going to go into an error model that then determines the error range on a temperature series for a region or a grid box, then onto a region, then finally onto a large-scale average. And the bias we're currently using for urbanization is this, of 0.06 degrees Celsius per century. This is based on comparisons of rural and urban networks in a few regions of the world. So this is the network of stations we have. So it was separated into, based on a US categorization of land use around observation sites. Also using night lights, so information from space, looking where lights are on at night. And so these are categorized as urban stations. These are categorized as rural stations. And then these are categorized as some in-between semi-urban, small town category. And if you then do the analysis of gridding these data and interpolating them to grids and working out the average, then you produce series like this from the 19th century through to the near present. And this is for the Northern Hemisphere land and Southern Hemisphere land. The full series is all the stations in black, and the various categories of urban, rural, and semi-urban essentially produce you the same series back to about the beginning of the 20th century. In the Northern Hemisphere, you have more variability because the coverage is sparser in the 19th century. In the Southern Hemisphere, it's less good, but there's obviously less land, and there's more issues of coverage as we go back in time in the Southern Hemisphere. But you're still getting much the same result from the 1930s onwards. Just as one example about we all been to London, and these are just time series of temperatures. This is maximum temperature, daytimes and average temperatures and nighttime temperatures, going back for several locations in and around London, back to the 19th century. And if you just concentrate on the middle one and look at the site at St James's Park, which is the observing site is near Horse Guards parade end of St James's Park. And this shows this is the orange curve, the year-by-year temperatures, and then this smooth curve. And then these two sites west of London, at the Botanical Gardens at Wisley and at the Rothamsted Agricultural Station in green, you've got their temperature trends. Rothamsted's a bit cooler because it's higher. But you see that overall, the trend of temperature at St James's Park is no different from the trend of temperature at Wisley and Rothamsted. So London is warmer than it would be without London, but that difference hasn't changed since 1900. And several big European cities show this. So it's not clear that population or development growth is a great metric for looking at urbanization trends. But certainly in Europe, you've got to be more careful in using that. It might be that other metrics in other parts of the world, in developing parts of the world, can be used. But again, really, you've got to look at each site and look at the differences each site, and rather than try and aggregate lots of things together. And it's best to try and develop, as I was saying earlier, these rural networks and urban networks and to compare the two. I won't talk much about interpolation to grids, but it's necessary to try and to do this, to stop the data being biased to areas which have dense coverage. And we use a 5x5 latitude, longitude, degree grid. And essentially, it doesn't really matter how you do this when you're going to a hemispheric or a global average. And there's a number of papers have compared different ways and shown that you get essentially the same result for the large-scale average, irrelevant of how you've averaged the data together, be it to grids of varying sizes. What we do is we don't do any extrapolation or infilling of the boxes that don't have any data. Now, some of the other groups do that, and that may make a little bit of difference when those regions that you've infilled might have warmed or cooled more than the other regions. But it seems that when you try and then directly compare, say, our results or another group's results, ignoring the extrapolation, you tend to get roughly the same answer. So the extrapolation may make an issue in 1 or 2 years, but it doesn't make any effect on the long timescale trends. This is then the comparison now. This is probably a difficult plot to look at, but you've got the near present here, about 2010, and back at 1850 here for the globe, the Northern Hemisphere and Southern Hemisphere, and the various series are on here. And this yellow, light green banding is our error estimate that encompasses between 2.5 and 97.5% range, according to this scheme that was developed by Philip Browan and others. So this takes into account the homogeneity adjustments, the biases, and the spatial coverage changes through time. So in the Northern Hemisphere, for example, the availability of data reduces as you move back before about 1950 and gets more acute as you get back into the 19th century, and it's more acute in large parts of the Southern Hemisphere today. Now, the point I wanted to get across here, though, is that there's our data and the 3 versions of one of the American groups at the National Climatic Data Center in Asheville, North Carolina, and the Goddard Institute for Space Studies in New York series here. But there's 2 series here from this one American group. One is in purple and one is in orange. The purple series uses their adjusted data, and the orange series uses their unadjusted data. And within this plot, the purple and orange series are there. And there's virtually no difference in the long-term trends or the trends over recent periods between the purple and the orange series, sort of confirming what I was saying earlier, that the effects of adjustments to the stations for the changes in sites and observation times doesn't really make any difference at these large scales. The reason we do it is that people use the data at individual grid boxes, and they would like that to be right as well, rather than just the large-scale averages. We did some work back in the 80s, as I mentioned, and this is the same type of plot. And we adjusted that time about 10% of the data. And in this analysis, I've taken away those stations, or I've unadjusted those stations. So I've removed them as red, I've unadjusted them as blue, and this is the globe, the northern hemisphere and southern hemisphere, and you can see that until you get back into the 19th century, you don't really see the differences between the lines. This is that 2.5 and 97.5% range again. Finally, on this little set of plots is, with the Met Office's help, we released about 80% of the station data that goes into this land analysis at the end of January last year. And the analysis with all the stations, 100% of the stations, is in black, and the 80% is in red here. And you can see that these series for the Northern Hemisphere, Southern Hemisphere, hardly diverge until you get back into the 19th century. And for our next version of the data set, which we're probably going to call CrewTem 4, we'll be releasing all the station data. And we're doing that by contacting the various Met services and making sure that we can release our versions of their data. I've probably not got much time, but I just wanted to, the error analysis is described in these couple of slides. It's fully described in this paper in Broen et al. In Journal of Geophysical Research. And as I say, the important bit, the important contributions to the error estimates are the errors due to the biases and the errors due to the error due to the sampling, lack of sampling back in time. The homogeneity adjustments have a very small error, and the urbanization bias is relatively small as well. Now, in the 1980s, when we came along, we were not the first people to produce these land records going back in time, combining lots of stations. This has been done. Vladimir Kirpin, who developed our climate classification we use today, produced an analysis in 1881, here in purple. And there were several other workers, Callender in the 1930s, Herd Willett in the 1950s, Callender again, Murray Mitchell, Budico. So there's lots of other people who have produced these series, obviously much more painstakingly than we were able to do it in the 80s, because they had to do everything by hand. And, but they produce essentially the same answer here in terms of the change of temperature from the 19th century through to the 1940s, and something of a slight lowering of temperatures since that time. There's a new analysis being done in the States at the Berkeley lab in California. And they've entitled their data set the Berkeley Earth Surface Temperature, so they can get this nice acronym. And this is a plot they've produced, which is on one of their websites. They say it's preliminary. This is using 2% of their data, and I'll show you what 2% means in a minute. And then this is comparison with the GIST data. Had CREW, this is incorrect. They've got the wrong acronym here, and the NOAA data set. They should be using CREW-TEM, which is the land-only part, because this is a land-only data set. But as you can see, their analysis in black on the year-to-year variability agrees with the green one and with the blue and red series. What they mean by 2% is 2% of the data. So their other plot shows you the locations of that 2% of the data, which amounts to 333 sites. And this is their spatial anomaly map for 2009, which they've got an anomaly for the globe of 0.64, which must be an anomaly. They don't give a base period, which must be to the overall period. You can see that this 2% is 2% of their data, sampled not quite randomly, but probably in accordance with the numbers of stations they have. So you can see there's a lot more dots here over the US, because they've got a lot more stations over the US than anywhere else. But essentially, they're going to probably get the same result as everyone else when they write their work up. We've done some of this sampling as well, and this is the same type of thing. Whereas you take the full network in black, and you've got 5 different networks, which are each a fifth of the data. So A is a completely different set of stations from B, and so on, C, D, and E. And so even if you take just a fifth of the data, you effectively produce the same series. So this is telling you that the number of stations that you're using to compute hemispheric and global averages you've got a redundancy. There aren't that number of effective spatial degrees of freedom. The stations aren't independent of each other. This is at the large scale. This is at the monthly and annual time scale. That would be a different result at the daily time scale. But at the monthly and seasonal time scale, you can probably get away with about 100 to 200 stations across the world's surface if all you wanted was the global average or the hemispheric average. What we ideally want is this gridded data set to compare with other fields like precipitation and pressure. Just one thing, here is the same plot again. We took out Northern Hemisphere one here. This is all the stations, and this is without any stations in the contiguous United States. So it's taken out all American data apart from Alaska and Hawaii, and you effectively get the same series, at least back to about 1900. This is the same thing in the Southern Hemisphere now with Australia. You've taken out all the Australian data, and you effectively get the same series without the Australian data. And taking out all the Australian data from the Southern Hemisphere is a much more stricter extraction, because this is about half the data in the Southern Hemisphere is from Australia. Just in terms of density of stations is much higher there than it is in South Africa or South America. Now, the land is just one part, and so the marine part is obviously a much larger part, and I want to just briefly go through that and then conclude. So what we do is we combine our land temperatures that we've produced at Crewe in Norwich, and we combine them with the Hadley Centre at the Met Office, their sea surface temperature data set. And we're currently combining with a data set called HAD-SST2, which is they've got a new version now, HAD-SST3, but they've got improved adjustments, particularly around the period just after the Second World War, from this work of Dave Thompson and others in 2008, and also allowing for the greater volume of data coming now from buoys, drifting and fixed buoys, compared to ships in the recent 15 to 20 years. But effectively, the most important thing is their bias is this adjustment caused by the change from canvas buckets in around 1940 to engine intake measurements afterwards. And this just shows you that change to from 1980. In 1980, almost all the observations are coming from ships. By now, only about 20% are coming from ships. Most of them are being made automatically by these things, drifters, drifting buoys, or by fixed buoys. This is a map of SST. You can see the ships in blue and the buoys in red, or the fixed buoys are in grey here in the tropical Pacific. This is that month, May 2010. This is the temperature anomalies for that month, and you can see the ship tracks and the buoys. And then that is transformed from that raw observations to this interpolated map of SST, which is what we then combine with. So this is from their new work in terms of breaking down where the observations have come from. So the buoys coming in here in recent years. Then the engine intake measurements here in green. Then various types of buckets, which are now rubber buckets. They're better insulated, so they don't have this evaporative cooling. Canvas buckets, which have this strong evaporative cooling, and wooden buckets in the 19th century, which have a smaller evaporative cooling. So what you're doing to all this data is this overall adjustment here in terms of when it's all canvas buckets, you're making the biggest adjustment, which gets smaller as you get more wooden buckets, and that then it's now realized that there was more wooden buckets used, or canvas buckets used after the Second World War, so there's some more adjustment there. And in terms of what it looks like, the red would be the uncorrected sea surface temperatures, and the black is the corrected in this new analysis, and these grey areas are the uncertainty in those adjustments, partly because the uncertainty in the method, but also in the uncertainty in the assumptions you've had to make about how the observations were made. So this is the uncertainty with the buoys here in recent times and the uncertainty in the post-World War II period. Now, if you didn't make this adjustment, then you would increase the amount of long-term warming. This adjustment, which is the largest of all, actually reduces the long-term trend in temperatures. Marine data, you also have air temperatures taken by ships and by buoys. So it's a completely independent version of the sea surface temperatures. It should agree quite well. And this is comparing with land. This is in a smooth mode. And you can see you've got land, sea temperatures in blue, and marine air temperatures in green. And you can see that they're showing the same overall course of trend since the 19th century. This warming up in the first part, slight cooling in the middle part of the century, and a warming since. So how we do the combination, I won't go into that in too much detail. It's basically in terms of the error. Then we might next time try some other ways of doing it and doing some comparisons, but it doesn't make much difference. And this shows you now the combined data set. This one in black, the UK data set, and then the two American ones, which are the same land versions as we saw earlier, but they've been combined with their own sea surface temperature data, which has been analysed in the US. And you can see that you're showing much the same sort of course of temperature change over this 150-year period. And the differences between the series are mostly within the error range that we've calculated by the techniques from Philip Browen's paper in 2006. There are other ways of estimating temperatures. These are the three main groups that do this. There's also a Russian data set, there's a Japanese data set, and the Chinese are doing one as well. And there's also this other data set I mentioned, the best analysis at Berkeley. But there are other ways, and a lot is made about the temperatures of the lower part of the atmosphere, which we call the troposphere. And these are measured by satellites looking down using their microwave sounding units. And this is a comparison here of monthly data from 1979 through to the end of last year. And that's in blue here. That shows a trend over this 32-year period of 0.16 degrees Celsius per decade. Then there's two of these satellite estimates, one by the University of Huntsville in Alabama, in red, 0.14, and RSS, Remote Sensing Systems in California, 0.16 degrees Celsius per decade. So exactly the same as our one. This one is not significantly different either. So the surface and satellite records agree, and 2010 was exceptionally warm in all these records, comparable with 1998. And just showing you this diagram just highlights a number of features about the variability of temperatures on the global scale from year to year. So these big fluctuations where the world warms up a lot are El Nino events. So the biggest El Nino event of the 20th century was 97, 98. We had a big El Nino event recently in 2009-10. And then these events where you get cooling relative to the line are La Nina, are major La Nina events. And some of them are the effects of the explosive volcanic eruption of Mount Pinatubo in the Philippines. So a lot of the variability over this short time is caused by El Nino, La Nina events, by volcanoes and other circulation features. So calculating trends over short periods is fraught with danger because you could be starting with an El Nino year and ending with a La Nina or vice versa. But overall, over the last 32 years when you've got this record, they're almost in perfect agreement. So in conclusion, I've talked about these the very different data sets. The land series agrees with the marine data. The biases are far more important than individual estimates of homogeneity at specific sites. The major biases are in the marine data. Here the adjustments raise the temperatures before 1940 by about 0.4, and there's strong agreement between the surface and the satellite records of temperature the satellite records begin in 1979. I'll finish there. Thank you very much.
Well, good morning, everybody. And I'd like to thank Alan Howard for asking me to come here and talk about effects of carbon dioxide on climate. I'm from the University of East Anglia too. I'm an oceanographer, and much of my research is on the global carbon cycle. So that's what I'm doing here. Here's the outline of my talk. I want to concentrate on three quite specific questions. And first, is the present increase in carbon dioxide that we see in the atmosphere man-made, or could it be natural? Secondly, what reasons do we have to think that carbon dioxide might be important in climate and climate change? And thirdly, are those reasons consistent with what we know about the past climate change and past carbon dioxide variations? So three fairly simple points. This is the first one, then. Could the present increase in carbon dioxide that we're measuring in the atmosphere be natural? This is a graph of ice core records, the tops of ice cores, with carbon dioxide measured in the interstices of the ice, and a timescale put on this from 1000 AD up to the present day, several ice cores, in fact, and it's married up here with the measurements made by Keeling at Mauna Loa since 1957. And the question then is, could this increase, which begins about in the late 1700s, about the time of the Industrial Revolution, and is continuing today, could it be natural, or must it be man-made? It has to be man-made. There's not really any doubt about this. Okay, why do I say that? We can calculate quite easily, because we know how big the atmosphere is, how much carbon dioxide is going into the atmosphere, must go in every year to cause this increase. It's about 4 billion tonnes of carbon per year as CO2. I write that as 4 gigatons of carbon. You'll see that you'll see that a number of times. So that's what's accumulating per year in the atmosphere. We could also work this out relatively easily. We know how much coal we produce, we know how much oil we produce, and gas. We burn about 7 to 8 billion tonnes of carbon per year from fossil fuel, and less certainly we release perhaps 1 billion tonnes from deforestation. So 8 or 9 billion tonnes per year. The total amount, now, where could this CO2 be coming from? It's been suggested, for example, that it might come from volcanoes, perhaps land plus undersea volcanoes. The total amount of carbon dioxide coming out of volcanoes is reasonably well known. On land and under the sea, it's at most a few hundreds of 1 billion tonnes per year. Now, that's a lot of carbon dioxide. Even a few hundreds of 1 billion tonnes is several tens of millions of tonnes. But it's not a lot when it's compared to the amount that humans are currently producing. And I've looked at the literature on this. I find that, the amounts of carbon CO2, there isn't really any disagreement, because we're all using the same estimates, the same literature values. And these two numbers are simply several hundred times apart. Similarly, the estimates of uptake or release from sedimentation, from carbonate and silicate weathering are all less than 0.1 billion tonnes. So they cannot be due, the 4 billion tonnes going into the atmosphere can't be due to those kinds of natural sources. Well, could the rise in the atmosphere be coming from the oceans? we have quite a number of ways of working out how the net ocean atmosphere flux. By my count recently, there are actually 7 different independent or quasi-independent ways of doing this. For example, we can measure the total excess amount of carbon dioxide over and above the natural marine carbon cycle in the oceans. They can do that surprisingly accurately. The measurements are accurate to 0.05% in the total amount of CO2. And this was done through the 80s and 90s during what's called the World Ocean Circulation Experiment, a major survey of the world's oceans. We can measure the flux across the ocean surface everywhere and all the time. Again, it needs millions of measurements. It's been done over a period of decades. It's a bit less accurate. We can measure the rate of oxygen decline in the atmosphere, and we can use that to put limits on how much carbon dioxide is going into the oceans. Or we could use various types of models, and all these methods agree fairly well that about 2 billion tonnes per year is going into the oceans, so not coming out. This just shows you, for instance, the picture of the excess CO2 in the oceans, where it currently lies. This is the result of the World Ocean Circulation Experiment. You can see much of it is in the North Atlantic, because that's where deep water forms, much more of it in the Southern Ocean. We can add all that up. We get the total amount of excess CO2 in the ocean. It's about 120 billion tonnes. And this shows you the flux of carbon dioxide through the surface ocean. Again, there are several million measurements gone into this picture, which is well known to us oceanographers. The red areas are where carbon dioxide is actually coming out of the oceans, in the equatorial Pacific, for example. The blue areas are where it's being taken up. If you integrate, average over all of the whole area, you get the net flux, and it's into the oceans on the order of 2 gigatons, 2 billion tonnes. So, it's not coming from the oceans. Could the rise in CO2 be coming from the land surface? Well, we still have to account for 2 or 3 billion tonnes of human-produced carbon dioxide, and the most likely fate for this is that it is actually being taken up by the land vegetation. The evidence for that includes, where else can it go? A budget of the whole system. It's not going into the oceans. Only 2 gigatons is going there. We need somewhere else. It has to be the land, really. It's consistent with the pattern of decline in atmospheric oxygen. I'll show you that in a minute. And it's consistent with studies that try to use the distribution of carbon dioxide in the atmosphere to work out where the sinks are for carbon dioxide. So our best guess is that the land is probably also taking up carbon dioxide at the moment. And this just shows you, this of course is the Keeling curve, which is very well known for carbon dioxide increasing in the atmosphere. There's also the South Pole is plotted here. Less well known is that since 1990 we've been able to measure the oxygen concentration in the atmosphere to sufficient precision to be able to see the corresponding signal, and it's declining slowly in the atmosphere. There's still plenty of oxygen to breathe, but it is going down a few parts per million per year, and the rate at which it is going down is consistent with this increase being caused by burning of fossil fuels. It's hard to see, if this was coming out of volcanoes, why the oxygen content should go down in that way. So this is what we think is happening to this anthropogenic carbon dioxide. The sources are about 1 billion tonnes from deforestation, 7 or 8 billion tonnes from fossil fuel. The fates of this CO2 are it stays in the atmosphere, it's taken up by the land vegetation, or it goes into the ocean. And just to show you which parts are well known and which parts are less well known, the fossil fuel source is well known. We can count it up by how much we burn. The amount that stays in the atmosphere is well known, and because we can measure that really rather accurately. The net uptake by the ocean, as I've said, is fairly well known, not quite as well known. These two, this source and this sink, the vegetation sources and sinks are much less well known. But these are currently our best guesses for this decade for how these sources and sinks balance out. About, of the more or less 9 billion tonnes released, about 4 is staying in the atmosphere, about a quarter is going into the land, and about a quarter is going into the oceans. So could the present increase in CO2 be due to natural causes? I think the answer is no. It simply can't be. It has to be due to man-made causes. It's the only source that's big enough. Okay. So what reasons do we have to suppose that carbon dioxide is important in climate? And in my view, at least, practically all of the evidence of the good, solid evidence for this comes really from the theory and the physics of radiative transfer and what we know about the composition of the atmosphere. Now, radiative transfer is the study of how radiation, light from the sun, and the heat radiation from the Earth gets through the atmosphere. The calculations are straightforward, and it's been known since the early 20th century how to do these calculations. They're tedious calculations. That in order to do it correctly, you have to integrate or average over all of the wavelengths that are of interest, and the gases, the greenhouse gases, such as carbon dioxide, such as water vapor, have many absorption lines, 60,000 in the case of carbon dioxide alone in these regions. So it's a detailed calculation. You need a lot of data to be able to do that from laboratory measurements. You have to account for the effects of temperature and pressure, which change the absorption very considerably, and you need more laboratory measurements for that. And then you have to integrate or average this calculation over all levels in the atmosphere and all different directions at which the radiation is going. So it's hard work. This just shows you a fine resolution look at the carbon dioxide absorption spectrum in its 15 micron absorption region. You can see, if you look hard, how many absorption lines there actually are. So these calculations are called line-by-line radiative transfer calculations. And they need big computers, and they take a long time. Fortunately, you can make approximations which are guided by the line-by-line calculations, and these approximations are perfectly fine for most purposes. Simple band absorption models can give surprisingly good results, and the original calculation of the greenhouse effect done by Arrhenius in 1896 was not too far off, amazingly. And he used, I think, a 9-band model. He didn't have any of this data. Simple modern approximations that are a lot better can be done on a handheld calculator. When we do those calculations, we find that the CO2, that if you double the so-called climate sensitivity, you double carbon dioxide from the pre-industrial level to the modern level in the atmosphere, you get about a little bit over 1 degree of warming if you just count the carbon dioxide absorption. You have to add to that the effect of water vapor, because as the temperature at the surface goes up, the water vapor concentration increases, and water vapor is a strong greenhouse gas. So water vapor has a residence time in the atmosphere of only a few days. It's quite different to carbon dioxide, which is in the atmosphere which effectively has a residence time that's measured in decades to hundreds of years. The water vapor is set entirely by the temperatures and conditions near the surface. Globally, evaporation has to equal precipitation, what comes out from the oceans and the land surfaces as evaporation must come back down as rain or snow. And during precipitation, the relative humidity has to be close to 100%. So what that means is that large regions of the atmosphere have to have their relative humidity close to 100%. And what that means is that as the temperature increases, the amount of water vapor must increase rapidly. Now, this is clearly observed in the present atmosphere. We see there's a lot more water vapor in the tropical atmosphere, and there's a lot more precipitation in the tropical atmosphere than there is in the polar regions. This can, of course, be wrong. We don't have to, it doesn't have to be the case that the relative humidity has to be exactly the same, or it can be wrong. In broad outline, it's hard to see how it can be a long way wrong. So when we add in the water vapor effect, we get more like a 2 to 3 degrees centigrade climate sensitivity to doubling CO2. There are a huge number of uncertainties in this. There is much that's not known about how the climate reacts. I've not mentioned clouds, other feedbacks, redistribution of heat by the ocean, etc. And so different climate models give different results, different ways of doing these calculations, different results. The IPCC, for example, quotes the climate sensitivity as in a range of 2 to 4.5 degrees centigrade. And it's also quite clear that factors other than carbon dioxide certainly influence the global climate. If we go back in time, the position of the continents, the type of vegetation, quite a number of other factors clearly influence climate. So finally then, is this consistent with what we know about past climate change and past carbon dioxide concentrations? Well, we are sure, we have a difficulty when we ask the question, what's the carbon dioxide concentration in the past? We are sure of the carbon dioxide concentration of the atmosphere only over the period of the ice core records, the Antarctic ice core records, which go back for less than 1 million years. During that period, there's a very close relationship between Antarctic temperature, specifically Antarctic temperature, and global and CO2. And that's consistent with our estimates of climate sensitivity for doubling carbon dioxide. And it therefore suggests that carbon dioxide, because it has changed over that time period, is important in natural climate change in that time period. It's clearly not the only factor, absolutely clearly not the only factor that's important in climate change. So this shows you, I'm sure we're going to see more of these records during today. This is the combination of ice core records from Antarctica, the carbon dioxide concentration in the Vostok and Epica ice cores going back 650 billion years, and the local temperature proxied by deuterium in the ice. And so we see this close relationship between these two variables. We see that as the character of the glacier, these are the glacial cycles going back in time. These are warm periods. We're in a warm period now. This is an interglacial. This is an interglacial. Before 400,000 years ago, the interglacials appear to be less warm, and the carbon dioxide concentration, sorry, this is the CO2, and this is the temperature. The carbon dioxide concentration tracks that. So the relationship between CO2 and temperature over this time period remains stable, as it were. If we look in detail at, this is just the warming of the final warming at this point here, up here, which comes into the present warm period. In detail in another ice core, this is carbon dioxide in that ice core. This is temperature proxy in the ice core. And we see that they relate to one another extremely closely. There's an 80 part per million change in CO2 occurring over 6,000 years here. So this is a fast change of carbon dioxide in the atmosphere by natural standards, but it's 100 times slower than we are currently changing carbon dioxide in the atmosphere. And you can see that the CO2, there's a lot has been written about the degree to which this signal lags or leads the temperature signal. So the CO2, does the CO2 change before the temperature or after it? It appears to change after it by a few hundred years. This lag is very uncertain, and it could be zero. It's very model dependent because this is measured in the gas, in the bubbles in the ice core, and this is measured actually in the ice itself, and you have to be sure that you properly adjust between those two. It's certainly consistent with the idea that CO2 has strongly amplified this temperature change, but it's not consistent at the moment, at least, with the idea that the CO2 initiated it. In other words, the CO2 change does lag the temperature change, but most of the time when temperature is increasing here, it's being accompanied by increasing carbon dioxide. We can go further back in time. This is some estimates of carbon dioxide in the atmosphere over the entire Phanerozoic eon, which is the last 550 million years or so. We have the lines are models, excuse me, and the dots are proxy estimates of what the carbon dioxide might have been back in those time intervals. As you go back in time, the sun gets less bright, and these models predict more carbon dioxide in the atmosphere. The other reason that, as we come back here, we're now 300 million years ago and earlier, in this period, which is the Paleozoic, you also have, there's no land plants or few land plants on the continents, and the weathering rate of rocks is slowed down because of that, and because of that, the carbon dioxide, these models predict a higher carbon dioxide concentration. But we have to be very careful with these models. I know the green one is my group's model, so I know these models intimately, and they are not data. They are schematic, very approximate ideas for what might have happened. Neither are the dots data in the sense of being actual measurements of carbon dioxide. If we ask the question, what do the data tell us about how CO2 has varied in the past? The answer is there is no data. There are no data for carbon dioxide at direct measurements beyond the ice core records. We have these scattered proxies, which, if we make some bold and rather uncertain assumptions, can give us can tell us something about what the carbon dioxide concentrations might have been. Those proxies include some ideas about the chemical composition of rocks that are assumed to have been laid down in contact with the air, counting the stomata on fossil leaves. It turns out that if you grow a plant in high carbon dioxide concentrations, it tends to have fewer stomata on its leaves. If that relationship holds over 300-400 million years, then you have something, possibly a way of telling how much CO2 is in the atmosphere. So these are uncertain proxies. And what do the models tell us? Well, all the models, these are models now, not models of the climate, but models of the past carbon cycle. Well, these models are very schematic. They assume, they have a simple climate model in them. They assume that carbon dioxide, that if you double CO2, the temperature goes up by about 3 degrees centigrade. In other words, they incorporate in them a climate, a simple parameterization of the climate change. And they assume that that climate change is important in setting the rate of weathering of rocks, and that in turn is what sets the CO2 level in combination with how much is coming out of volcanoes. The models are they use heavily smoothed curves because there's, generally speaking, not much data to constrain them. So it's frequently been said, for example, by people looking at these curves, oh, there's no Ordovician. We know that there's a glaciation in the Ordovician, but the CO2 was high, so this shows that CO2 is not important in climate. Well, that's to completely misunderstand how these models work. These models are not consistent with an Ordovician glaciation. You can quite easily put an Ordovician glaciation in. I've done it here by increasing the weathering, perhaps due to a mountain building or perhaps due to evolution of the first rooted plants, which occurred in the Ordovician. And it'll bring the CO2 down in the space of 1 million years because CO2 will change quickly on those timescales. And this big change here is due to essentially the biological invention of trees and vascular plants with deep roots. That's mostly what causes this decrease in these models. We can go even further back. There's, of course, no data and some very speculative theories about climate change back at that time. There are major glaciations 720 to 570 million years ago. And it's been speculated that they may be caused by very low carbon dioxide, and then the whole Earth freezes over, snowball Earth, and in order for the snowball to melt, the carbon dioxide has to go up to extremely high levels. This is frequently misinterpreted as saying, oh, there was lots of CO2 in the Neoproterozoic, and yet there were major glaciations. But that, again, is just simply completely to misunderstand what these rather speculative theories are saying, which is that the CO2 is what melts the glaciations, not what, and it's not high CO2 at the time that the glaciations occur. So, to conclude, the current increase in atmospheric CO2 is due to human activities, and I'll be pleased to eat my hat if that's not true. There is good reason to believe, but it's not absolutely certain, that if we change carbon dioxide levels by a factor of 2 from pre-industrial levels, this will substantially change global climate. It will substantially warm it. The reasons are it's consistent with the physics of the problem as we understand it, and that's really the main reason. It's consistent with what we know about past changes in CO2 and climate, although we know less, perhaps, than some people think we do. And such rapid global change, and this is important, is very rare in Earth's history. There's perhaps 1 or 2 other occasions when we think such a rapid global change may have occurred. You frequently see, especially in the last glacial period, some very rapid regional changes. You do not see rapid global changes. When the North Atlantic is cooling, which it does according to the Greenland ice core records, and warming very quickly at times, the southern hemisphere is in opposition and is doing the opposite. It is cooling, it is warming when the north is cooling, etc. And that's because it's a redistribution of heat around the system. But increasing CO2 in this way, such as we are, causes a rapid global change of probably 3 degrees for a doubling. So thank you.
Oh, thank you. Yes, the heat arriving from the sun must be radiated back into space. And you can calculate that that will happen if the radiating surface is at minus 19 degrees centigrade. So why are we not freezing cold? And the answer is the greenhouse gases protect us. This has been realized for a very long time. How does it work? Because of the greenhouse gases, the atmosphere is opaque to heat. You may think the atmosphere is clear. You can see through it. but for heat, it's like inky water. It's black, and it radiates like a black body. But the radiation only comes from the outer surface. That is currently at about the level of the Matterhorn. The heat from the ground cannot get out because the ink is too thick. From the Matterhorn level, the atmosphere above is thin enough for the heat to get out, and that's the level at which the temperature, on average, is minus 19 degrees. Now, if you put in more ink, the atmosphere gets thicker, and the heat can't get out even from the Matterhorn. The radiating layer goes up to the level of Mont Blanc. Now, there's a temperature gradient in the atmosphere, the adiabatic lapse rate, 1 degree per 100 meters. And if you're with the Matterhorn situation, you calculate down to ground level, minus 19 on the Matterhorn is plus 15 at ground level, which is rather comfortable. But if it's minus 19 on Mont Blanc, you'll be plus 20 at ground level, which is getting quite warm. Now, there's no limit to this process. Some gentlemen here, professors even, have told us that it is limited, but there's no limit. If you put in more ink, the heat from Mont Blanc won't be able to get out. The radiation level goes up further, and it can go up and up and up. Suppose it goes up to airline level, minus 19 degrees where planes fly, it'll be plus 25 at ground level, too hot. And this can go on and on. And what's more, there's positive feedback. If it gets warmer, you have more water vapor, which is a greenhouse gas. Less ice and snow, so less sunlight reflected back into space. CO2 released by the oceans when it gets warmer, methane release from the Siberian tundra. All these things increase the effect. So the system is unstable. It can oscillate between tropical heat with lots of CO2 and greenhouse gases, or to the ice age with very little. And historically, many times, the Earth has flipped from ice age to tropical heat and back again. It's unstable because of positive feedback. Into this unstable system, we are injecting greenhouse gases. We are pushing the world over the slope down towards tropical heat. This is the situation now. It's just beginning to roll. And you see the signs. They've just been presented. And this is the situation tomorrow. A runaway chain reaction is very likely. Whatever you may say today, it'll be very hot in the future. Thank you.
Thank you, Mr. Francis.